Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at the AGMA method for stress and strength. This is a continuation video from part one, which was presented right before, and this video is part of a lecture series on mechanical design too. So just to summarize what we've done in part one of these videos on the AGMA method, um, we found the bending stress for the pinion and the bending stress for the gear. And now what we're going to do is we're going to find the contact stresses, and after that work to find the factors of safety based on the power transmitted. So we're going to start this by writing the equation down for contact stress, and then we'll call back the problem at hand and kind of solve it based on this. But the contact stress can be found through the AGMA method by sigma C. So we usually write it as sigma sub C for contact. And we have, once again, two different units, US units and SI units. And we're really only going to focus on the US units equation, but the SI units equation is there for information. And we see that it's CP times the square root of WT, KO, KV, KS, KM over dP times F times CF over I. So there's a few different components that we have that are different. One of them that's an interesting component is dP is the pitch diameter of the pinion. So dP is the actual diameter of the pinion only. So some of the new things that are included in this are that CP is the elastic coefficient. We've already seen what CP is, and we know that CP is available as well in our formula sheet. Then CF is a surface condition factor. DP is the pitch diameter of the pinion, which is essentially just the diameter of the pinion. And I is a geometry factor for pitting resistance. So it's not the same thing as J, so it's a different term, but we'll have to find I. And that basically gets us to starting where we need to start in terms of solving this example problem that we have at the top of the page. So going further than this, we can recall that sigma P was equal to 13,924 and sigma G was equal to 9,975 PSI, and we'll use that later on in this video to solve some problems, to solve the whole problem and to solve the safety factor. So I just rewrote sigma C in terms of to the power of the 1/2. It's exactly the same equation, just a slightly easier notation to look at. So it just means square root as well. And what I want to do now is, because we've already started this problem in part one, there's a few different things that we already have checked off that we've already looked for and found in the previous video. So specifically, we found WT, KO, KV, KS, KM. We know the diameter of the pinion and we know the face width as well. So we're left with finding only 3 terms. So it's going to be a little bit faster now that we've already found most of the terms for this video. We're left with finding CP, we're left with finding CF, and we're left with finding I. Okay, so CP, based on the question, so we're going to go to the question and kind of look at what we have as information there, and then go to our formula sheet to find CP. So in the question, we're told that the gears are grade 1 steel through hardened at 200 Brinell. So if we go back to our formula sheet, we'll see that for elastic coefficient, we have different materials such as steel, iron, bronze, and tin bronze, and aluminum bronze. And we find that steel has 2,300 PSI to the power of 1/2. So we're going to use that value. Now remember that if you have two different materials meshing together, then you would have a slightly different way of finding CP. You could find CP through the handout and go to the handout and use this table 14.8 in order to solve for CP. So moving forward with this, if we now go ahead and solve for CP, we said that CP based on our formula sheet is equal to 2,300 PSI to the power of 1/2. That's the unit for this. Now, the next thing we're going to look for is CF, which is a surface condition factor. Okay, And I'm not going to talk much about this surface condition factor. So we already wrote down that it's called the surface condition factor. If we go to our formula sheet back again, we'll see that CF is just equal to 1. So typically the CF factor is not used much. If you do condition the surface with a certain treatment, sometimes there's a different CF number, but it's not something that we're going to concern ourselves in this video series and lecture series. So we're just going to say that this is equal to 1. The last one is I, which is our geometry factor for pitting resistance. And for I, we're also going to go to our formula sheet and kind of look at the different factors that we need to take into account for this. So going back to our formula sheet, we can go to our geometry factor for contact. So you can see that it tells us that it's a contact geometry factor. So we're given two different equations. We're given an equation for internal gears and an equation for external gears. So one thing you would think is, do we have internal gears? Do we have external gears? And what does that mean? So internal and external gears does not mean gears that operate outside and gears that operate inside. It actually means the direction in which the teeth are faced. So if I go back to my analysis here, I'm just going to describe my internal versus external. So external gears would be a gear that has gear teeth facing the outside, and then internal gear would be where teeth are facing inside. So some of the times that we use internal gears are when you use gears that are facing inside with other gears that are within the circle and rotating around. And an example of this is a planetary gear system where you would have, for example, 3 gears rotating around this system as is. This is a very rough diagram, but it explains what we have. So in this case, we do not have internal gears. We're usually always going to deal with external gears, but there are some specific cases, such as these planetary gears, where we actually have an internal gearing system. So I, from the formula sheet for external gears, is equal to cosine of phi sine of phi over 2 m sub n times mg over mg plus 1. And remember that mn is going to be equal to 1. Mg is going to be equal to the gear ratio. So it's going to be 48 over 16 in this case for our gear ratio between the gear teeth. And we get that mg is equal to 3. Now our pressure angle is 20 degrees in our problem, so we're going to use 20 degrees. And we find that our value is equal to I is equal to 0.1205. Now, if we go really quick back to our formula sheet, just want to show you really quickly that our value for Mn is called the load sharing ratio, and this value of Mn is equal to 1. So we just use a value of 1. And you can read more about it if you want to in Shigley's mechanical design book if you want to learn about this, but usually it's always equal to 1, and it's the amount of load sharing that occurs in that system. Okay, so moving from there, we can now solve for sigma c p and sigma c of the gear. And we need a specific one for gear and pinion because we have slight differences between the two. Now, we have a lot less differences than when we have our bending stress. So if we look at our problem, the only difference comes from Ks. So Ks is different for pinion and gear. Okay, so since Ks is different for pinion and gear, we're going to have a different value for sigma c. Now, sometimes you'll assume that ks is equal to 1. That's an assumption that you can make, especially if you're under time constraints. And if you assume that it's equal to 1, essentially your sigma c and for pinion and gear would be exactly the same. So really quickly, we can solve for sigma c pinion. So I'll write out the full equation for this one so that we have the full equation. And then for the gear, I'll just write the gear value itself. So, but I'll actually solve it a little bit differently just to show. So I'm going to erase it for now. So we have sigma CP is equal to 2,300 multiplied by 787.8, and these numbers are recalled from the last video, times 1 times 1.196 multiplied by 1.088 multiplied by 1.2225 divided by 2.667 multiplied by 2. And a note is you always use a pinion diameter here, regardless of whether you're using the pinion or the gear. And then finally, you have 1 over 0.1205, all to the power of 1/2. And if you solve for this, you get a value for sigma c of the pinion. You get a value of 101,663.2 psi as your stress. Now, to find sigma cg, what we could do is obviously we could run the whole equation again with a slight change in ks that we have. Another way to do it is to say, well, we can actually simplify this problem, and this is going to become something very useful if you change only one parameter. If you change only one parameter, what you can say is you can actually, and you'll have to think about this for a moment, but you can pause the video and kind of figure it out. You can say that ks of gear over ks of pinion to the 1/2 multiplied by sigma cp will give you your sigma cg. Okay, because the only difference between your sigma cg and sigma cp is the ks. So we can factor out that number and multiply by sigma cp to find the value. So we find that for the gear, we get 102,082 psi. Very close number. And this is usually the case in contact stress because it has more to do with the contact rather and the shape of the tooth and the way the tooth is made rather than the shape of the actual gear and the size of the gear. So we have a smaller difference here than in our bending stress. So that solves our contact stress as well as our bending stress. So now we have all the information. So what we're going to do next is we're going to introduce strength and what strength means and how we can compare strength to stress to make sure that our gears are strong enough. So we're going to do a little bit of theory on strength first, and then we're going to continue our working problem. So let's talk about bending strength first. Okay, so if we talk about bending strength first, what we can say is that we're going to have two different types of problems that we're going to have to solve for. Okay, and the first type of problem we're going to solve for is given a safety factor. So we're given a safety factor that we have to achieve, and we would be asked as designers for a minimum allowable strength. So in order to make sure that we have enough strength, essentially we would be told you need a safety factor of 2. What is the strength that you need to get that factor of safety? Now the second type of problem, and this is the problem that we have now, is we have all of the information available to solve for strength. So we're already given a material. And we are asked to determine if this material is good enough. and if the material has enough strength, essentially, or determine if the safety factor is high enough. So in our case, in our problem, we are actually told that we want to, so if I go back to the problem at the start of, of our video, of our notes here, we are told that we want to determine the corresponding factors of safety. So that means that we're going to find a factor of safety for bending and a factor of safety for contact. Okay. And in the question, we're also told the material for the gear and all the information from the gear to figure out the strength of the gear. So we know the strength and we know the stresses, and then we can compare the stresses to the strength and figure out, do we actually have a good factor of safety or not? And it doesn't really tell us to analyze the factor of safety, it just says to find it, but we're also going to like look at it and make sure that it makes sense to us as a design. If it doesn't make sense to us, then we need to make a change to the design to make it more reliable. Okay, so going back to our notes here, so we have the strength information, and what we're going to find is, because we have two different types of failure modes, contact and bending, we're also going to have two different types of strengths that we're going to calculate. So one strength is going to be S sub F, which is a strength against bending fatigue failure. So we're finding a strength that is essentially working against fatigue failure. And S sub H is a strength that is working against pitting failure, which we had talked about in earlier lectures in this module, where we talked about pitting failure and bending failure as something that we're trying to avoid. And the SF and SH are actually they're actually not strengths, but they are safety factors. Okay, so this is a safety factor. Okay, so this is the safety factor. SF and SH are safety factors based on the strength. The strength is actually a different term, so that's a correction to what I just said, but hopefully it'll make sense. So these two are safety factors, and we can write our safety factors as SF is equal to S sub T times YN over KTKR divided by sigma bending. Okay, and what we essentially have here is we have three normalizing terms. So these are normalizing terms, and they're correction factors. And what we're analyzing is essentially, if you take out the correction factors and said, for example, they're all equal to 1, you were basically writing that the safety factor is the strength over the stress. If the strength is greater than the stress, then you know you're safe. If the strength is lower than the stress, then you know you're not safe. And so S sub T stands for allowable bending strength in this case. Same thing with S sub H. So if we write S sub H, we would now look at the contact. And for contact, we have SC times ZN times CH over KT, KR, with all those correction factors as well, over sigma contact. And this SC would be our allowable contact strength. Okay, so now that we have the equations, we can start solving for our safety factor. So we already have, so let's start with bending. We already have sigma bending, okay? We already have our stress. So what we need to look for is ST, YN, KT, and KR. So we're going to go step by step, and we're going to learn what YN, KT, and KR are, but we're going to start with ST. So ST is the strength. So how do we find the strength? Well, the strength, we're told that we have grade 1 steel in the problem, and we're told that it has a hardness of Brinell of 200. So based on that, what we can do is we can go to a catalog for steel, or we can go to our formula sheet, and within our formula sheet we have some values for allowable bending strength and allowable contact strength, and we're given some for grade 1 steel and grade 2 steel. TH stands for through hardened, which is the case, and so we're going to use the grade 1 steel equation. We're also going to use this one for SC later on, so we'll keep it in mind, but we're going to solve for S sub T. Okay, so we need to use 77.3 times 200, which is our hardness Brinell, plus 12,800. So I'll write that out into our notes. So we have ST is equal to 77.3 times 200 plus 12,800, which gives us a value of 28,260 psi. And we also know that the material for the pinion and the gear are the same. So we have that ST sub P is equal to ST sub G. Okay, so then the next step we need to do is we need to find the YN value. Okay, so the YN value is a stress life factor. And what the stress life factor is a correction factor for the amount of cycles that a gear should go through in its life. So whenever we look at safety factor, we have to count that its life might be longer or shorter depending on its uses. And what the AGMA method does is the AGMA method assumes that the design and the safety factor is calculated for 10 to the 7 cycles, or in other words, 1 million cycles. Okay, it's made for 1 million cycles, and it says, well, for 1 million cycles, if we have 1 million cycles, your ratio of ST over sigma, and I'll put a B here for bending, over sigma bending should be at a factor of 1. It should be correct. So essentially, YN should be equal to 1 for 10 to the 7 cycles. Now, once you start increasing those cycles, you start getting more wear and more strength wear. So you have a little bit less strength than you would for 10 to the 7 cycles. So we need to correct for the fact that if we increase the cycles from 10 to the 7 to higher, we would have a YN that is a little bit lower to lower the strength a little bit. And what we have is we have a chart that we can use to try and figure out our information. So we're going to use a chart in our handout, and we have a ZN chart and a YN chart. The ZN chart works in exactly the same way as the YN chart. It's just a slightly different chart. And we also have equations that we can plug in directly. So sometimes it's easier to use the equations. You can use the chart or the equation. It's up to you. But we have this information. So given this information, we now need to figure out, well, how many cycles are we asked to solve for in our set of in our question. Okay, so going to our question, we can go back to our question and see how many cycles does it want us to work for. And here it says 10 to the 8 cycles. Okay, so we see that we have 10 to the 8 cycles. So that means that a gear tooth is going to hit 10 to the 8 times on our smallest gear, and we'll talk about that in a second. Okay, so that means that if we go back to our formula sheet, we are looking for 10 to the 8 cycles. Okay, and 10 to the 8 is here. Remember, this is a logarithmic scale, so just be careful with the scale. And if we go up here, we have a band of, we have a band of availability between here and here. Okay, so we can see that we have a shaded area. And it says here, the choice of yn in the shaded area is influenced by pitch line velocity, gear material cleanliness, residual stress, and material ductility and fracture toughness. So it's an arbitrary decision to make. Now, what gear designers will tell you is some of them will always choose the worst case scenario, which would be the lowest value. Okay, that would reduce the strength the most. And other people will tell you just use the best value because in the end you have a safety factor that should help you out as well. So what we're going to do, and this is a personal decision and it can be modified, is we're going to choose, at least when we do example problems, we're always going to choose the highest point. So I'm going to choose this point right here. Okay, and obviously it's very hard to tell what that would actually be, but it's going to be around 0.97. Now, another thing we can do is we can plug it into the equation of this line. So if you plug it into the equation of this line, you actually get 0.977. Okay, so we can actually plug into the equation as opposed to looking at the graph. It's up to you whether you want to look at the graph and just find a value on the graph or solve for the equation. The equation is going to be a little bit more accurate. So going back, we're going to write that yn is equal to 0.977 for 10 to the 8 cycles. And by 10 to the 8 cycles, we mean that essentially the life is going to be 10 to the 8 cycles. So one tooth will hit 10 to the 8 times. Now, what's important is to go back to the question and figure out, is it a tooth from the pinion or is it a tooth from the gear? So if we go back to our question, we see that it says assume a pinion life of 10 to the 8 cycles. So we're going to have to think about this one a little bit. So the pinion is going to hit 10 to the 8 times. So we're going to write YNP. Okay. Now, YNG is going to be different than P. So let's think about gear life a little bit. Okay. So gear life, let's say we have our gear pinion system with 1648. Okay. And we know that our gear ratio is 3:1. Okay. So NG over NP is equal to 3. Okay. That means that for every rotation, every full rotation of the pinion, how many rotations does the gear do? The gear does only 1/3 of a rotation every time a pinion does a full rotation. So if the gear life if the pinion life is 10 to the 8 cycles, that means that the gear life is actually going to be 10 to the 8 cycles divided by 3, or divided by the mg essentially. Okay, because you're only going to have a tooth in the gear hit every 3 rotations of the pinion. So there's going to be 3 times less contact for your gear teeth as opposed to your pinion teeth. Okay, so that means that the YN is going to be slightly different from your pinion one. So YNG, if we looked at the graph, we would get 1. Okay, if you actually look at, let's look at it really quick just so we have the information and we can see it. So 10 to the 8 over 3 would be 3.33 times 10 to the 7. This is 2 times 10 to the 7, 3 times 10 to the 7, so it's going to be very close to there. And if we look at this value, it's essentially and very, very close to 1. If we then plug it into the equation, we get a slightly different number than 1, but very, very close indeed. So we're going to keep it at 1. So we can say it's 1 from graph, or we can say that YNG, which is a value we're actually going to use in our calculations, if we use the formula, would be from the equation would be 0.996, so very close to 1. Okay, so we solve for Yn, so we're good to go on the Yn side. The next thing we want to do is find KT. So KT is a temperature factor. KT is equal to 1 for temps under 250 Fahrenheit. Now, if you have a temperature above 250 Fahrenheit, the book will have a value for that, which can be found. But we're going to keep it at 250 Fahrenheit for now. Now, we're going to keep it as if it's under 250 Fahrenheit, and most examples within this course will be under 250 Fahrenheit, so we don't really have to worry about KT. The last one is KR, and KR is a reliability factor, and it's based on the reliability that your system has, okay? And we're told in our question, if you go back to our question prompt, that our reliability is 0.9. So if we go to our formula sheet, once again, we have a summary for our reliability factor. And we can see that for our reliability, we can solve for different values for reliability based on these equations right here. So we have these equations right here, and we use the first equation if we're between 0.5 and 0.99. So if we plug into this equation, we would get our reliability factor. If we're between 0.99 and 0.9999, we would use the second equation there. So in the end, if we plug the values in and we find a reliability factor from formula sheet, we would get that KR is equal to 0.832. Okay, and this would be for an R of 0.9 within the equation, okay, or reliability of 0.9. So moving forward from that, we can then solve a safety factor for the pinion and a safety factor for the gear, because we have different sigmas as well as different strengths. We have the same strengths, but we have different YNs calculated for both. So SF of P is going to be equal to 28,600 multiplied by 0.977, and I'll write the values for both here, divided by 1 times 0.832, all divided by 13,924, and we can see that that gives us a value of 2.41. And then our safety factor for the gear would be 28,600 times 0.996. So a much better reliability, much better YN, because we have less cycles happening on the gear tooth, divided by 1 times 0.832, all divided by 9,975. So we also have a lower sigma here. So we end up with a safety factor of 3.43. And we can see that a safety factor of 2.41 or 3.43 is actually very good. So we're good to go, and we're happy to go ahead and run with that. Essentially what this means is that you have 2.41 times the strength required to not fail. And you have 3.43 times the strength to not fail in bending, not in contact. So now we need to solve for contact. So the last part of this problem is to solve the same thing for contact. So what we're going to do is we're going to use the SH equation, which is our safety factor in contact, is equal to SC times ZN times CH, divided by KT KR, which we already have. So we're already good to go here. We can say that we have KT KR. We can find SC very easily. And then we're going to divide all of this by sigma C, which we already have as well. Okay, so let's solve for SC really quickly. I'm not going to go back to our formula sheet, but we have, for grade 1 steel, we have a value of 322 times 200, or HP, plus 29,100, which is going to be equal to 93,500 PSI. And then ZN we're going to use the table to find Zn. Again, you can use the table or you can use the equation on the table. So we're going to go here and go to our Zn table. It works in exactly the same way as our Yn table, so I won't go into depth, but essentially you would have 10 to the 8 for the pinion, 3 times 10 to the 8 for the gear, and then you can solve for values here based on the chart itself. So slightly lower values in Yn, but if we actually work out the values with the equation given in on the chart itself, we get that Zn P for the pinion is 0.948, which is lower than the gear, makes sense. And then Zn for the gear is equal to 0.973. Okay, then the next term is called CH. Now, CH is a gear-only factor. And I'm going to add it to our notes. So I'm going to add that this is for gear only. So whenever you're solving for SH for the pinion, do not use CH, okay? Now, based on that, we then say CH is for gear only, and it's called a hardness ratio factor. Okay, and we're going to use, we can go use a chart for this, but essentially, if HBP over HBG is less than 1.2, then CH is going to be equal to 1. And this is something very important. So basically, if you have the same materials in your pinion and gear, then CH is equal to 1. CH would be a different value if your pinion and gear have different hardnesses. So what happens in real life is that usually the safety factor of the gear is higher than the pinion, and therefore what we do is we try to design the pinion to compensate for its lower safety factor. So what we can do sometimes is we can have a higher hardness on the pinion than the gear in order to counter the fact that the pinion rotates more times and the teeth hit more times than the gear. So that's why we have this hardness ratio factor only for the gear. So let's go to our formula sheet really quick just to go see where this information is on CH. So we have CH at the top here, and we have some equations associated with CH. So we can see that CH is equal to 1 plus A prime times mg minus 1, and A prime is equal to 0 when HBP over HBG is less than 1.2. And then we have some other equations to find A prime, and then we can plug into that equation. Okay, so that's one way to do it, is to use the equation, especially if you're using Excel or something like that. You can definitely use the equation, but there is also a chart available to us. So if we go to the chart, we can see that at the bottom right, we get the rule that when HBP over HBG is less than 1.2, we use CH is equal to 1, and if not, we have this neat little chart that we can use to find the CH factor much faster than using equations. So you can see that the hardness factor is there. And again, this is a gear-only system. Okay, I'll write it here too so that we have it. It's gear-only, making sure that we don't forget that. Okay, so going back to here, we have this, and then we can solve for SHP and SHG for the pinion and gear. So for the pinion, I'm going to write the equation out without the CH, even though the CH is 1, so it doesn't really matter in this case because we have the same hardness for pinion and gear, but we're still going to not write it out because we clearly understand that it's not part of it. So we have 93,500 multiplied by 0.948 not multiplied by 1, and then divided by 1 times 0.832, sorry. And then all divided by our value of 101,663. And then our second value is our second equation. We can plug in everything except we'll add the CH. And I'm not going to write it out, but we'll write the answers out. So we have 1.048 and 1.071. Okay, so what do we see from here? Well, we see that this is very close to failing. So even though we were just asked to find the 4 safety factors and we were asked to sort of just find them and that's it, we definitely want to make sure that we would redesign the system with a higher safety factor. Okay, so we need either more strength in the gear, or we need to modify something about our system to increase the safety factors. Okay, so let's summarize the problem, and then we'll add one more little theoretical detail that is important for practice problems and for understanding what safety factor means, because there is always more of a limitation in contact than bending, so we need to take into account something a little bit extra. So going back to the question, we've been able to solve through the last 2 parts that we determine the AGMA bending and contact stresses, so those are sigmas, and then the corresponding factors of safety if 5 power is to be transmitted. So we were able to find the 4 factors of safety of SFP, SFG, and SHP and SHG, and we were able to show those safety factors based on the power transmitted. So the last thing we're going to do is we're going to add a quick aside to this, that sometimes the questions won't ask for a safety factor, but they will ask for something called a design factor. And what a design factor is very much similar to a safety factor. So remember that your safety factors are SF and SH, okay? Your design factor essentially is a way of finding SF and SH in one number as opposed to having 2 numbers as a limit, essentially. So whenever the question asks for to check if the system works with a minimum safety factor, or what the material would be, for example, for a safety factor, it could ask it for a design factor and then work with the design factor directly. So SF is, so the safety factor in bending is equal to the design factor. So for example, if I told you that the design factor in a question is equal to 1.5, this would mean in the question that SF is equal to 1.5. And then SH would be equal to the square root of design factor. So if I'm looking for a safety factor in contact, when we use design factor, the contact would actually be the square root of 1.5. Okay, so it would be a little bit lower than 1.5, essentially, the requirement that we have. Okay, so this concludes all of the theory that we need to learn on stress and strength and the AGMA method. What we're going to be doing in the next video is going through a full example exam or problem that we would ask in an exam, for example. And obviously, if you were given a 1 hour time frame, or even a 1 hour and 15-minute time frame, or a 50-minute time frame, you wouldn't be asked to solve a full AGMA problem because it could take quite a while. It is possible to do, but it could take quite a while. So now what we want to start doing as engineers is to start looking at problems and figuring out how do we change some of the factors in order to help us improve the design. And this is really what engineers and designers have to do. So in the next video, we're going to do a full problem in context of industry and what you would actually do in industry with this methodology rather than just solving the methodology step by step. And this is going to be similar to how you would be evaluated in a class like this. So this is a good starting point to see how you would get evaluated in an exam in this type of class. So we'll see you in the next video, but this basically concludes all of the theory. And now we're going to do one more example after to understand. And then Shigley's mechanical design has a lot of study problems that I'll make available to you to study and work on so that you understand how to use this type of problem. All right, we'll see you in the next video.